Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 5.2 on systems of linear equations in three variables. So everything in this section is just an expansion of what we were covering in section 5.1, as now we move to linear equations in three variables. And so instead of ax plus by is equal to c, the equations we're going to be dealing with this time around are of the form ax plus by plus cz is equal to d. In other words, we're introducing a third variable of z. This does mean we've moved into three-dimensional space now, which is not something we're going to spend a lot of time focusing on because it's beyond the scope of Math 101, but just to give you a rough idea of what's going on, even though this is still called a linear equation, if you were to graph this, it wouldn't be a line anymore. It would be a flat plane like a piece of paper in three-dimensional space, and we'll see some pictures of that a little bit closer to the end of the section to illustrate the different ways that these equations can interact with each other. A system of linear equations in three variables then would look something along the lines of this. So when we were working with two variables, x and y, we needed two equations in order to pin down a unique solution. Now that we've moved into talking with three variables, it turns out that we're going to need three equations to pin down a unique solution. And that's just a general rule of systems of equations. If you have fewer equations than you have variables, you can't come up with a single unique solution. Which doesn't mean you can't work with it, and we'll take a look at an example of how to handle two equations with three variables a little bit later on. The solution to a system of linear equations in three variables then is an ordered triple x, y, z instead of an ordered pair x, y, and this ordered triple has to satisfy every equation at the same time. So to be a solution to the system in the previous section, it had to make both equations true at once. Now it's going to have to make all three equations true at once. Much like in the previous section, let's start with an example of how you would double check your answer once you get one. So in example 1, we're asked to verify that the ordered triple -1, 2, 4 is a solution to the following system of equations. And remember that the order here is still important. When we were working with ordered pairs, it was always x first, y second. When you're working with ordered triples, it's always x first, y second, z third. It's just alphabetical order. And so now what we need to do is essentially check this in each of the equations and make sure it checks out. So if we plug this into the top equation, x would be -1, plus y, which is 2, minus z, which is 4, and that should be equal to -3, which checks out because that's a -5 plus 2, or a -3, is equal to -3. For the middle equation, we have 2 times x, -1, minus 3 times y, which is 2, plus z, which is 4, and that should be equal to -4, which also checks out because this is a -8 plus 4, which is a -4. And then last but not least, for the bottom equation, we've got x, which is -1, minus y, so -2, plus 3 times z, which is 4, is equal to 9. And that also checks out because this is 12 minus 3, or 9 is equal to 9. So since this ordered triple xyz makes all three equations true, it checks out. It is a solution to the system of equations. And that's what we're looking for when we solve one of these. So let's talk about how to actually solve one of these systems then. And our choices are a lot more narrow than what we had back in section 5.1, where we had two methods. We had the substitution method and we had the additive method or the elimination method. Substitution no longer really works for three equations with three unknowns. It does technically work. You could make it work, but things get so messy and so convoluted that it's just not worth it. Elimination is by far the better approach for systems of equations of this size. And so that's what we're going to stick with. And our goal is to start with, you want to look for the easiest variable to eliminate. Truth be told, you could eliminate any of the three. And there's not always an easiest variable in the first place, but if you see that one has lower coefficients, or maybe it lines up really nicely where the coefficients match up, but they have opposite signs already, then you might just decide to target that variable first. It's just the easiest thing to work with. What you then want to do is use addition to eliminate the chosen variable from two pairs of the original equation. So let's say you focus on the variable z to eliminate. You would choose to eliminate z from two of these three pairs, equations 1 and 2, equations 2 and 3, and equations 1 and 3. By doing this, by picking two different pairs of equations and eliminating z, you have essentially created two new equations with only two unknowns because you got rid of z. And at that point, it becomes a problem exactly like section 5.1, a system of two equations with two unknowns. So then you would solve the system of two equations and two variables. That will give you two of your answers for your ordered triple. And then in order to find the third, just like in the previous section, you take those two and plug them back into any of the original equations. So you'll find it's kind of like a nested elimination. You start by eliminating one variable from two pairs of the three equations. That'll give you two equations with two unknowns. You'll use those to eliminate another variable, which will give you one equation with one unknown. And then you can do what's sometimes called backward substitution. You'll take that one solution, plug it into one of your equations with two unknowns. You'll take those two solutions, plug it into one of your original equations with three unknowns. So this probably sounds pretty abstract at this point. Let's take a look at some examples. So in example 2, we're asked to solve this system of equations. Now be careful whenever you copy down a system of equations like I'm about to do for elimination. Make sure that you copy it correctly. It's always worth double checking that you don't mess up any of the signs or any of the coefficients, because this type of problem is very sensitive to small mistakes like that. If I were to recopy this top equation down as 3x plus y plus 2z is equal to 14, the entire problem will be thrown off. So just keep that in mind. So as I start looking at variables and seeing which one's probably going to be the easiest to eliminate, the answer to that is probably the y's, because I see that these top two y's could be eliminated just by adding as they are, and in addition to that, these bottom two y's could be eliminated just by adding as they are. They line up really nicely. Again, I want to stress the point though, you could eliminate any of these variables, but eliminating x and z would just require a little bit more multiplication along the way. So let's say I label these equations so that I can refer back to them easily. The first thing I'm going to do is eliminate y from the top two equations. So from equations 1 and 2. And I can do that just by adding them together as is. I don't have to make any other tweaks. So we've got 3x minus y plus 2z is equal to 14. And the middle equation is x plus y minus z is equal to 0. And so if I add those together, we would get 4x. The y's would cancel, which is the point. 2z minus z would be a plus 1z. And 14 plus 0 would be 14. I'm going to come back to this equation in a minute, so I'm going to label this as equation 4. Now I need to do it again from a different pair of equations. So I can't use 1 and 2 again, because that would just give me the same result, but I can use any other pair, 1 and 3 or 2 and 3. In this case, as we already discussed, 2 and 3 lines up nicely with y. And you do want to make sure you eliminate the same variable from both, otherwise you're going to get stuck. I've already committed to y at this point, I have to stick with it. So now I'm going to eliminate y from the bottom two equations. So the middle equation, x plus y minus z is equal to 0, and 2x minus y plus 3z is equal to 18. And so if I add these two together, 3x, y's cancel, plus 2z is equal to 18. And this is now going to be equation 5. And so what we have now with equations 4 and 5 is a new system of two equations with two unknowns. 4x plus z is equal to 14, and 3x plus 2z is equal to 18. At this point, it becomes just like a problem from section 5.1. We solve these two equations with two unknowns for x and z. And at this point, if substitution looks like it would work nicely for that, feel free. Substitution would work okay at this point. Elimination also still on the table. Let's say I want to do elimination. I think the z's look the easiest to cancel out from elimination. So if I want to cancel out this positive 2z, I'm going to multiply this top one by negative 2. So if I do 2 times equation 4, that would give me a negative 8x minus 2z is equal to a negative 28. And the equation 5 I leave as is. 3x plus 2z is equal to 18. So what I'm doing now is I am eliminating z from my two new equations 4 and 5. And so if I add those together, that's going to give me a minus 5x. The z's cancel, and a negative 28 plus 18 would leave us with a negative 10. So if I divide both sides of this equation by negative 5, we have x is equal to 2. And now you just work your way backwards. So this is 1/3 of our final answer. I'm going to take this, plug it back into one of my equations with two unknowns to solve for z. So let's say we plug it into the top one. So if I plug this into equation 4, we've got 4 times x, which is 2, plus z is equal to 14. So that would be 8 plus z. So if I just subtract 8 from both sides, we get z is equal to 6. And so now that's 2 parts of our answer. I'm going to put boxes around these, but this is not the way our final answer is going to look, just so we don't lose track. So now that we've got x and z, we can plug that back into any of the original equations to figure out y. And just by looking at these, I think the middle equation is probably going to be the easiest in terms of the math. So now we plug this into equation 2. So we've got x, which is 2, plus y, which is the one we don't know because we eliminated that one first, minus z, which is 6, is equal to 0. So the 2 minus the 6 would combine to give us a minus 4. And if we add 4 to both sides, we get y is equal to 4. So our final answer, the solution to the system of equations, is an ordered triple x, y, z. We have an x of 2, a y of 4, and a z of 6. Let's take a look at another example, and in this one there's no way around it. We're going to have to do some multiplication to set up the elimination. So try pausing the video here and see if you can follow a similar method to what we did in the previous example to solve the system of equations. So once again, it doesn't matter what variable we choose to eliminate here. They'll all get you to the same answer in the end regardless, as long as you don't make any mistakes along the way. So just to mix things up, let's say I choose to eliminate x this time around. Well, if that's the case, I'm going to make use of this x with a coefficient of 1. That's just going to make my life easier. So if this top equation has a positive 4x, let's say I choose to make this bottom equation have a negative 4x. So I'm going to do negative 4 times equation 3 and I'm going to add that to equation 1 to eliminate x. All right, so if I do negative 4 times the bottom equation, that's going to give me a negative 4x minus 12y plus 12z, be careful with the signs, is equal to a negative 4 times a negative 10 would be a positive 40. And then I'm going to add that to the top equation, 4x minus 2y plus z is equal to 13. The x's cancel. We get a negative 14y plus 13z is equal to 53. If I want to make use of that x with a coefficient of 1 again, I can do that, but now I have to pair it off with the middle equation. So if I want to cancel out this 3x, I need to make this into a negative 3x. So if I do negative 3 times the bottom equation, and add that with the middle equation to eliminate x, we would get negative 3 times the bottom equation would be a negative 3x minus 9y plus 9z is equal to a positive 30. And then I'm going to add that to the middle equation, which is 3x minus y plus 2z is equal to 13. X's cancel, which again was the point. And we have a negative 10y plus 11z is equal to 43. So this is my new system of equations now. Negative 14y plus 13z is equal to 53. And negative 10y plus 11z is equal to 43. Now x was probably not the easiest variable to eliminate in this case, and the reason why is because the coefficients were slightly bigger than the coefficients of the other variables. So the numbers here are going to get fairly large, but that's not necessarily something we should be scared of because we have calculators to help out with this kind of thing. So it's not that big of a deal. So if I name these equations 4 and 5, I need to choose a variable to eliminate now. And again, it doesn't matter which. I'm going to choose to focus on the y, and the reason why is because 14 times 5 would give us 70, which we can make the bottom y 70 as well pretty easily. So what I'm going to do is I'm going to multiply the top equation by 5. That would give me a negative 70y, which means I need to multiply the bottom equation by negative 7 to get a positive 70y. So let's multiply that through. For the top equation, we've got a minus 70y. 5 times 13 would give us a plus 65z. And this is equal to 53 times 5, which would be 265. And now I'm going to do negative 7 times the bottom equation, which will give me a positive 70y. Again, be careful with your signs. Minus 77z, and this is a negative 7 times 43, which would be a minus 301. Now if we add this together, the y's cancel, that's the whole point. If we do a negative 77 plus a 65, that would give us a negative 12z. And if we do 265 minus 301, that would give us a minus 36. And that looks nice. Now you're not always guaranteed your final answers are going to be nice with the system of equations, but in this case this is promising. Because if we divide by minus 12 here for this one equation with this one unknown, we get z is equal to a positive 3. Now I'm going to take this answer and plug it back into one of equations 4 or 5, it doesn't matter which. Let's say I plug this into, let's go with equation 5, why not? we get negative 10y plus 11 times z, which is 3. 11 times 3 would be 33, is equal to 43. Subtract 10 from both sides. Divide by negative 10. We get y is equal to negative 1. And now we just need to plug both of those into one of the original equations to solve for x. And I'm going to choose the bottom one just because, again, x has no coefficient there. So if I plug both of these into equation 3, we're going to have x plus 3y, which is 3 times negative 1, so it's going to turn into a minus 3, minus 3 times z, minus 3 times 3 would be 9, is equal to negative 10. Add 12 to both sides. We get x is equal to 2. So the ordered triple that is a solution to this system of equations is an x of 2, a y of negative 1, and a z of 3. And keep in mind that if this were a test question, it would probably be a really good idea if you take this ordered triple and plug it back in, just like we did in example 1, to make sure it works. Right? So something you'll notice from this example is that even if the numbers start to get really big in the middle of the problem, that doesn't necessarily mean you've done something wrong. Sometimes that just happens. Let's take a look at one more independent system, one more system that has a unique solution. And the point of illustrating this one is that not all three equations need to have all three variables. If you take a look at this system, we've got x minus y plus z is equal to 7, so that one's got an x, a y, and a z. But in the second equation, we just have 2y minus 3z is equal to negative 13, so that one has no x. And then in the bottom one, we've got 3x minus 2z is equal to 3, so that one has no y. Well, essentially what this allows you to do is just skip one of the first steps of the problem. It's actually going to make the problem shorter overall. We've already got one equation that just has y and z, so no x. X has been eliminated. And we've got one on the bottom that only has x and z, so this one has no y. Y has been eliminated. So what that means is if we use one of those to take this top equation and either eliminate x or y, one of the ones that are missing in the bottom equations, then we will have a pair of equations that doesn't have x and y. So it does have to be x or y. It does have to be one of the variables that's already been eliminated in one of the other equations, because we want a pair that is missing the same variable. If you tried to eliminate z in this top one, you would have one equation with just x and y, but you wouldn't have anything to pair it with. All right, so at this point, it doesn't matter whether you choose to eliminate x or y. So let's say I choose to eliminate y. I can't use the bottom equation for that because it doesn't have one. So I'm going to need to pair off the top two equations. So I'm going to do 2 times the top equation and I'm going to add that to the middle equation. So if I do 2 times the top equation, we would have 2x minus 2y plus z, plus 2z is equal to 14. Careful not to lose focus halfway through. And then I'm going to add that to the middle equation, and I'm going to line everything up because we're going to combine like terms. So I've got 2y minus 3z is equal to negative 13. All right, and so now if I add those together, the missing x in the bottom equation is essentially equivalent to 0x. So when you add that, you just get the 2x that carries down. 2x plus 0x would be a 2x still. The y's cancel, which is the point. We have a minus z, and that's equal to a positive 1. So we created this new equation from equations 1 and 2, we can just pair that with equation 3, which is also in terms of x and z. We will already have two equations with two unknowns. So we're going to have a 2x minus z is equal to 1, and a 3x minus 2z is equal to negative 3. Now I need to eliminate one of these variables. I'm going to focus on the z because it has a nice coefficient of 1 here. So I'm going to multiply that by negative 2 so that I can cancel out the negative 2 at the bottom. I need to turn this into a positive 2. So that's going to give me a minus 4x plus 2z is equal to negative 2. And then I'm going to add that to the bottom equation, which would give me a negative x equals a negative 5, or in other words, x is equal to 5. I'm now going to plug that back into the top equation of my two equations with two unknowns system. So that's 2 times x, 2 times 5, which is 10, minus z is equal to 1. Subtract 10, divide by negative 1. And now what we want to do is find the value of x, or y. Y is what we're missing. So you've got options. You could either plug it into the top equation because you know both x and z, or you could plug it into the middle equation because just knowing z is enough for that one. Either one would be fine. The only thing you couldn't do is plug it into the bottom equation because there's no y to be had in that one. I think the coefficients of the top equation are really nice and small, so I'm going to go with that. We've got x, which is 5, minus y, plus z, which is 9, is equal to 7. So the 5 plus 9 would give us a 14. Subtract the 14 from both sides. 7 minus 14 would be a negative 7. Divide by negative 1. And so x, y, z, our solution to our system of equations here, our ordered triple. We've got a 5 for x, a 7 for y, and a 9 for z. All right, again, it's a little bit trickier, but in the end, it's actually a little bit less work than what we were seeing in examples 3 and 2. For the rest of the section, we're going to take a look at what happens when you don't get that one unique solution, when you're not dealing with a dependent system of equations. And it can actually play out a few more ways than we saw with just two equations with two unknowns, due to the nature of three things interacting with each other as opposed to just two. So the first thing we're going to take a look at is an inconsistent system, a system with no solution. And fortunately, that one works out exactly like we saw back in the previous section. So let's illustrate it with an example. We've got this system of equations, and this one is also lined up to eliminate y really nicely. So why don't we work with that? So again, I'm going to label the equations 1, 2, 3. I'm going to add equations 1 and 2 together to eliminate a y. So that would give us a 2x minus 2z is equal to 8. And then I'm going to add 1 and 3 together to eliminate a y. And this time around, the x's cancel, the y's cancel, the z's also cancel, and we get 0 is equal to 7. That's actually all it takes. If at any point along the way you get something that looks like this, something that is just not true, then the answer is no solution. It might happen in the first step when you're trying to eliminate one variable. It might happen in the second step. when you're trying to solve the system with two equations and two unknowns. But if any point along the way you get something that looks like this, no solution. This is what you're looking out for. Dependent systems, systems with infinitely many solutions, can actually play out a couple of different ways, which makes them a little bit more tricky this time around. So let's start by taking a look at one of the ways in which these can come together with example 6. And we've got the system of equations x plus 2y minus 3z is equal to 5, minus x minus 2y plus 3z is equal to negative 5, and 2x plus 4y minus 6z is equal to 10. Well, what it is that all of these equations are a multiple of each other, right? If you just multiplied this top equation by negative 1, you would get the middle equation. If you take the top equation and you multiply it by 2, you would get the bottom equation. In other words, if you tried to eliminate any variable in this case, so let's say you did 1 plus 2, everything would cancel. You would just get 0 is equal to 0. If you did 2 times the second equation and add it to the bottom equation, everything would cancel. You would get 0 is equal to 0. Even if you did negative 2 times the top equation and add it to the bottom equation, every combination of equations in this case would completely cancel each other out. That's because it's all the same equation. And so this corresponds most closely to the type of dependent systems that we saw with two equations and two unknowns, where the lines were actually the same. And so in this case, how we would write the solution is similar to the way we did in section 5.1. We would write x such that, and then we would just write out one of the equations that we're working with. So we could write x such that x plus 2y minus 3z is equal to 5. Because any ordered triple that satisfies this equation would also satisfy the middle one, would also satisfy the bottom one, because they're all just multiples of each other. Now this is different from what happens if you get something where everything cancels out when you're down to only two equations with two unknowns. That means something different in this case. So let's illustrate that. We've got this system of equations, 2x plus y minus z is equal to 1, so on and so forth. So let's start trying to solve this and see what happens. I'm going to choose to eliminate the z's in this case, just because all of these coefficients have pretty large numbers, but z's seem to be the smallest. So let's say I choose to cancel z from equations 1 and 3. So if I want to cancel out that plus 8z, I'm going to do 8 times the top equation and add it to the bottom equation. So if I multiply everything in the top equation by 8, be careful not to miss anything. And then I'm going to add that to the bottom equation. The z's cancel, which is what we're looking for. So we have a 6x minus 6y is equal to 18. And so now I need another pair of equations to eliminate z from. How about 1 and 2? So I'm going to do 2 times the top equation and add it to the middle equation. Double the top equation will give me 4x plus 2y minus 2z is equal to 2. Middle equation I'm just going to copy. So if we add those up, we get x minus y, the z's cancel, is equal to 3. And so now we've got a new system of equations. 6x minus 6y is equal to 18, and x minus y is equal to 3. And these two equations are now a multiple of each other. So we didn't get anything that completely canceled out when we were working with all three equations, but we're going to get something that cancels out now that we're working with just two of them. So if we do, you could do negative 6 times the bottom equation, which will give you a negative 6x plus 6y is equal to a negative 18. And if you add that to the top equation, everything would cancel out. You get 0 is equal to 0. So the answer is actually going to be infinitely many solutions, but it's not quite as simple as just writing out one of the equations from earlier. There are additional restrictions in play, and I'll explain why that is when we look at a picture of these planes on the next slide. For now, let's talk about how to write the answer. What we're going to do is we're going to write our ordered triple x, y, z, but we're going to let one letter just be the letter itself, and we're going to solve for the other two in terms of that same variable. Because my two equations with two unknowns are working with x and y, it's probably best here to either let x just be x or let y just be y. It doesn't matter which, both work okay. And on MATLAB, they'll have one of those fixed so that you'll know what letter you need to solve for. Let's say I want to write everything in terms of x. So I'm going to let x just be x. I need to figure out what y and z are then in terms of x. We do that by solving equations. So we know that x minus y is equal to 3. If we solve this equation for y, add y to both sides, subtract 3 from both sides, y would have to be equal to x minus 3. All right, so we've got x and we've got y now, both in terms of x. Now we need z in terms of x. And so now we go back up to one of the original equations. So we've got 2x plus y minus z is equal to 1. But y, we know, is x minus 3. And then I'm going to subtract the 1 over to the left and add the z over to the right. So this is going to be a 2x plus x, or a 3x, minus 3 minus 1, so a minus 4, is equal to z. And so z would be 3x minus 4. And so to write our answer then, we'll write it in set builder notation, right? This is the solution now because you can pick any value of x you want to. You could pick 1, you could pick 10, you could pick 1/2, and then this basically gives you a formula for finding the other two parts of the ordered pairs afterwards. And so in set builder notation, we would write it as our ordered pair, x, x minus 3, 3x minus 4, such that x is any real number. Meaning you could plug any real number in for x, and this formula, this ordered triple, would give you a solution to the system. So let's talk about what's going on here. I mentioned previously that these equations are planes in three-dimensional space. So a plane is kind of like a sheet of paper, but infinite. It goes forever in all directions. What happens is when you have a independent system of equations, a unique solution, the three planes represented by your equations intersect in exactly one point. What's happening when you have a dependent system then, infinitely many solutions, is that they're actually all intersecting in more ways than just that one point. In example 6, the previous one we worked, where all of the equations were just multiples of each other, it was all actually the same plane. Imagine you have 3 pieces of paper, but they're all just stacked on top of each other. In that case, any point on the plane would be a solution to the system. And that's why we represent the solution as just the equation of one of the planes. But what happened here in example 7 is a little bit more specific. What happened is that the 3 planes ended up intersecting in such a way that they don't overlap perfectly like they did in example 6, but there is an entire line where they intersect with each other. That's why it was when we were solving the 2x2 systems, the line equations, that we got 0 is equal to 0. And so now when we describe infinitely many solutions for a situation like this, like in example 7, the solution can't just be the equation of a plane anymore. That's not good enough. It has to be the equation of a line. But writing the equation of a line, you can't just do y is equal to mx plus b in 3 dimensions. That's why we have to do it in this ordered pair notation. That's what we've essentially done. By letting one of the variables be fixed and solving for the others in terms of that variable, you are creating the equation of a line of solutions in 3-dimensional space. And so that's what makes dependent systems with 3 equations with 3 unknowns so tricky. The thing to remember is that if all 3 of the equations are just multiples of each other, if all of the variables cancel out in the very first step, you just write the solution of an equation. If, on the other hand, variables start canceling when you get to the second step, once you have 2 equations with 2 unknowns, that's when you have to write the ordered pair, and you have to write all of it in terms of a single variable. So you have to handle each situation differently in this case. So let's take a look at one more example where we're going to have that same type of dependency. So we get a little bit more practice writing that ordered pair of solutions, that ordered triple of solutions rather. And what you'll notice here is they've asked us to solve the following system of equations, but they only gave us 2 equations with 3 unknowns. It's actually impossible to find a unique solution if you have fewer equations than you have unknowns. So there will be no unique XYZ ordered triple as a solution to this. In order to solve this system as best we can then, we start off with the same idea as what we did before. Our goal is to eliminate one of the variables from the only pair of solutions that we have. In this case, the z's are already lined up pretty nicely to be canceled. So all we have to do is add these 2 equations together. If we did, we get a negative 1x plus a 1y is equal to 3 minus 1, or 2. There is no other equation to be paired with this. We cannot narrow this down to one equation with one unknown. So at this point, we have a very similar setup to what we had when we got stuck in example 7, when we had 0 was equal to 0. What you do is you just let one of the variables be the variable itself. We solve for everything in terms of x in example 7, so why don't this time around, for a little bit of variety, we just let y be y. We'll solve for everything in terms of y. So y, we're just going to call itself. Now we can take our equation with 2 unknowns and solve for x. So if we just add x to both sides, y would be equal to x plus 2. But y is not what we're trying to solve for. X is. We want it in terms of y. So now I'm going to subtract 2 from both sides as well. And so x would be equal to y minus 2. So now we've got x in terms of y, we've got y in terms of y, so just like before, we're going to go up to one of the 3 equations, or one of the 2 equations with 3 unknowns, and just solve for z. So we've got x minus 2y plus z is equal to 3. I'm going to solve for z first and then substitute. So I'm going to subtract the x across and add the 2y across. But I want all of this in terms of y, so I'm going to replace x with y minus 2, which we now know it's equal to. But be careful, because of that subtraction now, that distributes through. So this would be a 3 minus y, minus a negative 2 would become a plus 2, plus 2y. Constants, we've got a 3 plus 2, which would be a 5. And then we have a minus y plus a 2y, which would be a 1y. So z would be equal to 5 plus y, or y plus 5, however you want to write it. So in this case, our solution would be the ordered triple, y minus 2, y, 5 plus y, such that y is any real number. All right, so once again, you just pick one variable to be itself, and then you solve for the other variables in terms of that single variable. To give you a picture of what's going on, because we had two equations with three unknowns in this case, we're still in three-dimensional space and we're still dealing with planes, but you can't get a unique solution out of this. The way they were interacting in this case was like this, so we got a line of solutions. It's also possible you could have parallel planes. So let's say you had one flat plane and then you had another flat plane that was just a little bit above that one. In that case, they wouldn't intersect with each other at all, so it is possible to get no solution out of an underdeveloped system like this. And it's also possible for the planes to actually be perfectly overlapped if the equations were a multiple of each other. So it's possible to get infinitely many solutions of that type as well. So everything is on the table for an underdeveloped system like this, except for one unique solution. And that is it for section 5.2. It is a very focused section overall. It is about solving systems of linear equations with three variables. That is the only type of problem in this section, is solving systems of equations. The tricky part with this section is making sure that you know how to handle the situations where there are infinitely many solutions. That's where things start to get a little bit complicated. So make sure you get some practice in with those types. And as always, if you guys have any questions, please make sure you let me know.